In the name of God and hi to all students. In this session, we want to study and be familiar with another method for dimension reduction. It named principal component analysis. At first, we must familiar with some basic stochastic definitions like variance. If these red dots are our data, as you studied and you learned before, we can calculate the mean of this data. We sum all of them and then divide it by n, yes, and we called it the mean of the data. Now we want to calculate the variance of this data. You learned the variance too, but at this moment we want to review these definitions. For example, if here is mean, then we calculate the distance before mean and each data, and then we powered it to 2. Okay, for each data we calculate this, and then finally we sum all these distances and then divide it by the number of the data. Okay, we called it a standard. We called it variance. We called this measured value variance, and we can rewrite it like this here. The formulation is this: sigma 2 is equal to the summation of the distances of each data from the mean of the data, then we power to 2 and then divided by n. And if we calculate the root, the square of this measurement, we called it a standard deviation. Then a standard deviation is equal to the square root of the variance. Now consider this figure. If we have two-dimensional figure and if we want to calculate the variance of these two dimensions, we can calculate the variance along x direction and along y direction. Okay, because as we saw in the previous slides, the variance is calculated along one dimension. Okay, then if we have these stars, we projected on x direction, that it is in green stars, and also we projected the stars along y direction. You can see here with red stars. Okay. On the other hand, we can calculate the mean of these blue stars, and the mean of them is this red circle. Okay, then the mean also can project along x direction and along y direction. Okay, then we can calculate the variance along x and the variance along y direction. How? Exactly according to the previous slides. Using this, along x direction we calculated the mean, then calculate this distance, calculate the summation of these distances divided by n, and then a square of this. Okay, and we repeated this measurement along y direction. Okay, then the variance is like this. Then before this slide, for two-dimensional data, we can calculate along each of the direction, along x and along y. Okay, and now if attention to the variance equation, it is like this. If we decompose this to two parentheses, it is like this. Okay, you see it. It is the first line can be rewritten in the second line. Okay. On the other hand, if you attention to covariance, and we introduce covariance, that I'm sure you know it. Covariance is for two-dimensional data and is related to two groups of data. Okay, x and y. Okay. And if attention to this, covariance of x and x is equal to variance of x. Attention to this equation. And covariance of x and y is equal to the covariance of y and x. They can be change the place of two variables. Okay. And now attention again to this two-dimensional data. Okay, in left we have two-dimensional data. You can see the distribution of the data, and in the right also you see it with this red star. This red is the mean of this two-dimensional data. Okay. And this is the equation of covariance. Then according to this equation that you can also see this equation here, you can calculate the distance of each data of in the projection on x direction and y direction. I mean, first you project the data to along x and project this data along y direction, and then also project the mean along x and y. Okay, then you calculate each x, the distance between each x and the mean along x and along y direction. Here the distance is negative. For this x1 is negative because x1 is less than or smaller than the average of x or the mean of x. And here also y1 is less than or smaller than the mean of y. Then this distance is less than 0. But on the right, the distance is in converse with the left. The distance between y1 and mean is positive. It is related, y1 is related to this area. Attention. And if x1 also related to this area, the distance is positive. But in the left figure, attention to the location of data. It is related to this area. Okay. Then according to the previous slide, the distance of x from its mean and the distance of y from the mean of y is positive. Then if we multiply these distances, the result of also positive. In this area, the both distances are negative. Then after the multiplication, the result of positive. But in the area of upper left and lower right, I mean here and here, okay, one of the distance is negative and another distance is positive. Then the result of multiplication is negative in this area and this area. Okay, and as you see again in this figure, the amount of positive value in these two areas are greater than the negative value in these two areas. Then the covariance of this data with this direction is positive. Then the relation of the data with this direction is positive. And then if we have data with this direction, the covariance would be negative. Again, we calculate the mean, we project the mean on x direction and y direction. We calculate the distance of each data, and then again, if we divided this and the whole area of data to 4 regions, then again you can see the data with this distribution, with this direction, has the negative covariance. Okay, and data with this distribution, the amount of positive value is the same the amount of negative values. The distribution is like a circle. Then according to covariance, according to this equation, according to the calculation of these distances, there is no any relationship between these data. Okay, and now if you want to rewrite the covariance with matrix representation, if we have x vector like this, okay, then we can calculate the covariance. At first we must calculate the average of this data. We called it x bar, and then I calculate the distance of x from and the distance of x from its mean, and then we transpose this matrix, multiplied the term of the first term, the first parenthesis by the second parenthesis, by the transposing of the first parenthesis, and divided by n. then it is covariance. You can write a matrix with some numbers and then calculate the covariance. Then finally we have this covariance matrix with this value in each array of the matrix. Okay, and if you attention, the diagonal elements are the variance. The diagonal elements are variance, and again, if you attention, the covariance matrix is symmetric, because you know the covariance of x1 and x2 is equal to covariance x2 and x1. Then it is symmetric matrix, and also it is a positive semi-definite matrix. What is the positive semi-definite matrix? It means that all eigenvalues is real. In the previous session we explained about the eigenvalues and eigenvectors, and we explained how we can calculate it. We can calculate these parameters. Then for the covariance matrix, the eigenvalues is real, the eigenvectors are orthogonal, and the eigenvalues are greater than or equal to 0. It means that the eigenvalues are not negative. Okay, they are 0 or greater than 0. And then we can write the covariance matrix can be diagonalized. It means that we can decompose the covariance matrix to this matrix. It is like the eigen right and left vectors, right and left eigenvectors that again we mentioned in the previous session. Okay, then totally if you compare the variance and covariance with each other, both of them is a parameter, is a measurement for the spread and the distribution of data. Okay, but variance is related to one dimension, and covariance is related to two-dimensional data. And then all of them, both of them, is related to the spread of data according to the mean, and also the covariance measure of how much each of dimensions vary from the mean with respect to each other. With respect to each other, it means that the direction with this state is negative, or the direction with this, the data with this direction is positive. Covariance has positive relationship. Okay, then again you see this positive relationship, negative relationship, and it is no relationship with according to the covariance criteria. Another parameter that calculate the relationship for two-dimensional is correlation, and the correlation of x and y is the covariance of x and y is divided by the variance of each data. Then correlation of x and y must be between -1 and 1. And for example, if you see this orange data, there is no correlation. It is again like a circle. Okay, but if you consider this pink distribution. This here, the correlation, the covariance is negative because of the direction, and then it is perfect negative correlation. Compare this with this. Okay, they are more dense. In the right, the data are more dense. Then the relation are higher. The relation of this data is higher than this. And if we quantify this relation with correlation, we can see the correlation for this is minus 0.3, but for this is minus 1. And for positive, again, attention to a blue diagram. Here is a perfect positive correlation. Then it is equal, the correlation is 1. But here they are wider, and the spread are wider. Then it is low positive correlation, and it is so. Okay. Now we review variance, covariance, and correlation, and in different diagram and figures we see, and we studied this parameter with their concept. Now we want to know what is the feature extraction. We said that PCA, principal component analysis, is the method for dimensional reduction, or reduction the dimension. But it is, the application is for feature selection. But what is the feature? What is the feature extraction? And then after that, the feature extraction, we have feature reduction. Okay. Consider feature extraction refers to the mapping of the original high dimensional data onto a lower dimension. For example, you have an image. Instead of analyzing and processing the image directly, you can reduce this high dimensional to only one vector. Okay, then we can extract the main features, the main characters of that features using different methods. For example, using Fourier, using wavelet, okay, using different methods. But this feature extraction can be done using some unsupervised or supervised setting. Unsupervised means the goal is minimize the information loss. We try to not to have the missing the information, and in the other side we can maximize the class discrimination. We can extract the features that using of them we can distinguish, we can recognize the features better with these features. Okay, then by graphical figures you can reduce this image. Okay, this is original, and this is the flattened. This vertical is a flattened image, for example. And then after that, by using a transformation, different transformation, we can reduce data. Okay, how we can reduce data? one method is PCA. But how? For example, you have 100 students. You measure the height, weight, hair color, average grade, red, the color of eyes, the thickness of hair. Okay, and then each student has these features. For example, my height is around 170. Each of you has your own height. Each of you has your own weight. Each of you has your own hair color. These things is your feature. Okay, then we measured this and we express this feature in a vector. We represent this feature in a vector and we call this vector feature vector. Okay, then as you see here, each student has a vector of data which describes him of length. For example, here, and the number of a student is 100. Then we can put each vector in one vector of matrix, one column of the matrix. Each vector can be placed in the one column of the matrix. Then finally we have the matrix with m by n. M is related to the number of features, the height, weight, color of hair, and n is related to the number of students. Okay, here we can see here again each column of the matrix is related to students. Okay, and the number of the rows is related to the number of features. Okay. Now, how we can and what features can we ignore? What features can be? The question here, what features can be ignored? For example, feature that is linearly dependent on other features. For example, the head size and height may be related to each other. Okay, and the thickness of hair, it is constant feature with some noise. Okay, then we can remove this. And constant, if we have some constant features, for example, in this example, it is the number of heads. Of course, it is not important. Okay. And on the other hand, which features, attention that what features can we ignore? It is related by removing of these features, the information preserved. These are by removing these features, we can gain access to the main characters of each student. And which features do we want to keep? Features that doesn't depend on others. For example, eye color. It means they are uncorrelated or uncorrelated, and the features has low covariance. And features that changes a lot. For example, the grades. Okay. Then, what is the most important features is the features with high variance and low covariance. How do we represent our data so that the most important feature can be extracted easily? Okay, this is our question at this moment. But we must to keep the data with high variance and low covariance. High variance and low covariance. Then the covariance is important for us. Then the base of the PCA is covariance. How we calculate the covariance of matrix? How we calculate it? We explain. At first, we calculate the mean. We calculate the distance of data from the mean of data, and then we calculate the covariance matrix. We explain it. X multiplied by X transpose. X, of course, these distances. X prime multiplied by X prime transpose, and then we calculate the eigenvectors and eigenvalues of covariance matrix, exactly like the method we explained in the previous sessions. Okay, we calculate the eigenvalues and eigenvectors. You see that we put this in, we explain it, put C in this equation, and then we determine by considering the zero of the determinant of this matrix, we can calculate the eigenvalues, and then after that, putting eigenvalues in this equation, we can calculate the eigenvectors. We explained it in the previous session. Okay, and now how we can calculate, how we can select the number of eigenvalues. We put it in this equation. Okay, 100 is multiplied by lambda j divided by the summation of all the lambda. Okay, and then for example we said that 90% is okay, 99% of this we is okay. Then in each application, according to the desired thresholding for accepting these eigenvalues, we can now and we can select the number of eigenvalues. Okay, and the number of eigenvalues is related to the number of features that we can select. Okay, then by PCA we can reduce the dimensionality of data and retain most of input data information, and useful for compression and noise removal in data. Then by information we mean the variation present in the sample given the correlation between the original variable. The new variable called principal component, and they are uncorrelated and are ordered by the fraction of the total information each retained. For example, then in this slide we can say that we try to remove the noise and redundancy. We said that redundancy means that the head size and height is related to the usher. Noise, measuring the thickness of hair is noisy data. We remove it, and then we keep the important data. Okay. This I have another slide here, but here I don't know why it removes in the PDF version. For example, if we apply the PCA and employ PCA on image, we decompose, we calculate the mean of the, we have a huge of data, we calculate the mean of data, we calculate the mean of the images, and then we calculate the distance of each image from the mean image. I explain according to this, if our data is images. And then we calculate the covariance, and then finally we calculate the eigenvalues and eigenvectors. Okay? And then if we reconstruct the images only using one image, it is like this. It is not clear. Using if we can consider only two eigenvalues, this is related here. 8 is related like here. 100 is related like this. Okay, then instead of, for example, 1000 images, we can put each image in one column of matrix and calculate the covariance, and then calculate the eigenvalues and eigenvectors of that covariance matrix, and then we reconstruct each image only using 100 features. And then if you compare this reconstructed image with the original image, they are very similar to each other. Okay, and now this is end. I hope you get and understand the concept of the principal component analysis, PCA. PCA is related to reference C, chapter 15, and in chapter 15 you can see the singular value, the composition we explained before, and also you can see principal component analysis. Also, another better reference for these topics is reference P, and the first chapter of this is related, the first chapter of this reference is related to singular value decomposition and PCA. This reference is better and is more applicable with compared to reference C. Thanks for your attention. If you have any question, please prepare it and ask in online classes. Good luck and bye.